Okay, we're going to continue on chapter 14. Sounds good. Why not? All right, so chapter 14, the final chapter of organic. Last several organic molecules we started talking about last time. We got into our friends, the carboxylic acid, I believe. And remember the functional group of a carboxylic acid doesn't look like that. Maybe it looks like this more so. There you go. So remember that this is the functional group here. This carbon-oxygen double bond with the OH group, again, sometimes written in formulas all together like COOH. As we talked about, because of the presence of both of those polar groups, the carbon-oxygen double bond and the oxygen-hydrogen bond there, it's able to hydrogen bond pretty efficiently. Again, it can hydrogen bond with something like water, or itself through the carbon oxygen double bond using somebody else's hydrogen and its oxygen. It could also hydrogen bond like normal through the OH group of as well. And that makes, as we talked about, really one of the few things that could sort of be an alcohol in terms of boiling points and melting points. This can do that. We get our carboxylic acid, as we know, from our primary alcohol that gets oxidized. We go way back when. And again, that's going to oxidize to our aldehyde. And that will result in our aldehyde being formed there from the loss of the hydrogens. It will then oxidize one more time, drop in basically the oxygen in there to our carboxylic acid. And again, making our functional group in this particular case. Obviously, as we also talked about, heading in the opposite direction is basically the reduction reactions of all of those. If you want to kind of go backwards, you would do your reduction reactions going backwards. In terms of naming these, really based off of the longest carbon chain, like pretty much most things that we talked about, it obviously does need to include the functional group. And because of the presence of this hydrogen there, much like the aldehydes, that group does need to be at the end of the molecule, one end or the other. Otherwise, hydrogen will have too many bonds. So what that means in terms of naming is we do not necessarily, or we do not really need to give the location of this sort of carbon oxygen double bond in the name. But for numbering purposes, as we talked about, it would be always carbon number one, whichever end it happened to be on. And that's important for any other groups that were sort of attached to it. If you had like this here, actually, we'll make that a two carbon Cl and CH3. So if we had something like this, again, this would be our carboxylic acid group. We'd be looking for longest carbons, which is 1, 2, and 3. That's based off of propane. We drop the E and we do add oic acid to it. And that is, again, how we go about naming our carboxylic acids. That would be carbon number 1, which means at carbon number 2, that would give us our chloral group there. So that would be 2-chloral propanoic acid in that particular case. Because they're an acid, as we talked about, they pretty much will kind of do regular sort of acid-base sort of reactions. Then when they dissolve in water, they'll do our kind of Bronsted-Lowry definition where they will donate over an H plus to the water. When they react with a strong acid, they'll do a sort of acid-base reaction where water and a salt is made. So these guys, again, if it's sort of going to just be dissociated in water, he's going to send over the H plus. And again, we'll make our acetate and our H3O plus, so our Bronsted-Lowry definition. Also, he can react with a strong base. And again, from our strong base OH and our H, we'll make our H2O. And then basically we'll make this salt, which again is an ionic compound. where kind of the sodium would be attracted to the negative guys. So these are a couple of those reactions that they can do. We also got into, I think at the end there, our other group that's very similar to this, and that is an ester. And an ester has a functional group very similar here, carbon, oxygen double bond to the oxygen. The difference is right here, there is no H, so it's a carbon containing group. And really, we make an ester, as we talked about, through an esterification reaction. And it's made by basically reacting a carboxylic acid and an alcohol. And I'll just turn the alcohol around this way. And basically what's going to happen is we're going to make water here. So we'll take out water. And basically we will push the carboxylic acid together with the alcohol part that's left. And that's going to give us our ester sort of connection, oxygen, again, to a carbon. And that arises, as we talked about, basically here. Kind of two parts to the ester when you put it together. So if we were going to take this guy, once again, we're just gonna kind of box our water there. And that's gonna give us water. And again, we're just gonna push these guys together. And I'm just gonna go underneath here. CH3, CH2, C double bond O to our O to our CH2 and our CH3. So when we talk about sort of naming this guy, it is basically you want to think about it how it comes together in this esterification reaction, and it always does come together between the single bonded carbon and oxygen. That's basically where you kind of squeeze everybody together. And what that means is, again, if you go away from that double bonded oxygen, that's going to give you the alcohol part of your ester. If you go towards the double bonded oxygen, that's going to give you your carboxylic acid part. And the way that we name these guys is the alcohol is pretty much named as a group. So in this case, that's a 2-carbon group, which would give us ethyl. We go off of this guy here, which is based off of propane or propanoic acid, and we put O8 at the end of it. So that's ethyl propanoate here. And that would be how we go about naming it. So you can either drop the I and put, you can either drop the IC acid from the carboxylic acid name, put 8, or go back to the alkane name and put O8, however you want to remember it, we'll do it. Any question on that there? All right, so I think that's where we laid up. So let's try one here. Why don't you write the balanced equation for the reaction of propanoic acid and methanol in the presence of heat and a catalyst? Okay, so let's take a look. So we're going to draw all this. So we'll go backwards here. Oic acid tells us it's carboxylic acid. Propane tells us it's 3 carbons. So we'll start with our 3 carbons. Since you are drawing it, you can draw the carboxylic acid really on either side. I'm going to put it here to the right. I'm just going to fill in the rest of my hydrogens that I need there. And that should be my propanoic acid. Methanol, OL, tells us it's an alcohol. Obviously, this part of it here told us it's a carboxylic acid. And methane means 1 carbon. So we're looking at really, and I'm going to turn again my alcohol sort of around so that the OH is sort of facing the carboxylic acid. If you know this reaction, that's a good way to do it because really you're just kind of setting yourself up to what to draw in the right orientation. In this case, this is going to give us our esterification. Remember, you might sometimes see an H plus written up on the arrow, and that's an acid catalyst. That's what that stands for, where it says like acid catalyst. Also, heat is sometimes represented by the little triangle sort of deal as well. And again, they're not really going to have that much of an impact on anything you're drawing, but again, if you see that up on the arrow, it's just really needed for this reaction to take place. Remember this, when you take carboxylic acid and alcohol, we're basically going to take out water, so might as well just put a box around it, and I'll draw underneath here. That's going to give us our water. And at that point, the reason we kind of want to set it up like this is really we set ourselves up to pretty much only need to copy what's left, and that's a good way to kind of do it. So we could just start to the left there and just copy exactly what I just underlined, which is essentially just taking the water out. That's going to give us our ester bond in this particular case. Question on that one. By the way, that would be called what, this ester? It Yeah, I think that's correct. So that is again going away from the double bond, right? And always looking around here. That's to our alcohol part, which is our methyl group. And again, going in the other direction through the double bonded oxygen. That's our carboxylic acid, which is based off of 3 carbons. And that's going to give us our methyl propanoate. Yeah. Any questions on that one there? So clearly you do need to know how to do this reaction. Yeah, draw the products, kind of write the reaction out and name it as well. Any questions on that? So as we talked about last time, I think as well, it's good to know like here, okay, I got a carboxylic acid, I got an alcohol. Again, before you even start, you should hopefully know you should get an ester. And again, just sort of knowing what you should get can oftentimes help you kind of draw it correctly when you have to draw it. There you go. That's hopefully what they got going on there. So we talked about here naming, but just to reiterate, that's where you want to look personally, between the carbon and the oxygen and go away. For our alcohol part, go through the double bond to our carboxylic acid part. Carboxylic acid part, again, becoming the base of the name, the alcohol part really named as a group. And although they've kind of all been drawn this way, clearly it works if it is flipped around the other direction as well. So once again, you want to look there and go away from the double bond to get to your alcohol. And obviously through the double bond there to get to your carboxylic acid. So even if it's flipped around, just kind of go in those directions to get the 2 parts that you need. All right, so this here, as we can see, we would break right about there, go away from the double bond. That's the alcohol part, which gives us our ethyl. This is the carboxylic part, which is also ethane. And again, ethyl ethanoate. Once again, breaking or looking right here. That's our alcohol part, as we just did there, and our carboxylic acid part going in that direction. And here we have, again, alcohol part, which is 2. So there's our ethyl. And that is based off of benzene, right? Going in the opposite way. And we put the O8 at the end of it. It's also based off of benzoic acid, really. And you drop the IC acid and put 8, and that's how we get to ethyl benzoate. There's some common names here. Ethyl acetate. You're not going to worry too much about that. I will say ethyl acetate. I'll spit it out there maybe. Ethyl acetate does pop up a lot, or that acetate. Again, that's based off of ethanoic acid, or acetic acid is that carboxylic acid that comes from. Here's some of the things maybe you'll make this week, I think. Aspirin, as you can see, ester group right there, carbon, oxygen, double bond, and oxygen, again, from our carboxylic acid here and our alcohol happening over there. Oil wintergreen as well, methanol, alcohol, and again, our carboxylic acid there, mace methyl saxylate, which is oil wintergreen. I feel like that's one of the ones you make, I think, if I'm not mistaken. You want to write the name for this one? Go for it. See what you come up with. All right, so let's take a look. So we'll start with the first one that was given to us. And again, obviously, you should be able to recognize our ester group right about there. And even for naming, that's a good place to focus in on. As I mentioned, a good place just to kind of think about breaking it there. And that's going to send it this way away from the double bond for our alcohol, which is 2. So that's going to give us our ethyl. And obviously going through the double bond there is going to give us our carboxylic acid, which is based off of propane. So propanoate here. So that's a little ethyl propanoate. Same thing if we look at the one I just drew there, we could see hopefully our ester group right there. Again, there's a carbon right at the end of the double bonded oxygen and going into that other oxygen. That means it works the same way if we're kind of playing with our line structure here. We'll kind of break it still there. We're going to go away from it to get our alcohol part, which should be to our right. That would be 1, 2, and 3 carbons there. So that's a propyl. Now, again, going through the double bond the other way is going to give us our carboxylic acid part. We do not want to forget this carbon. So that's 1, right? 2, 3, 4, 5, and 6. So that's based off of hexane. So that's a little hexanoic. Hexanoic, no, not so much. It's close. Hexanoate sounds much better. There we go. Based off of hexanoic acid. So propyl hexanoate there. Question on that. Now, if I drew this, now what would it be called? Same thing? It would be the opposite. I hope so, unless I've screwed up, but you're right. It should be the opposite. Now our ester group is heading this way, right? So now when we kind of go to our carbon oxygen double bond there, towards the away from the double bond is our alcohol part, which actually would then be 1, 2, 3, 4, 5, 6 there, which would then be hexyl. And over here would be our carboxylic acid part heading this way, which would be 3. So a little propanoate there. So it is important, especially in line structure, obviously where the double bonded oxygen is. And again, remember, it could head in both directions. So don't get turned around if it happens to be in the other way. Any questions on that there? All right. All right. So this guy here is going to be, what is it? I heard propyl methanoate, propyl ethanoate. So again, this is going to be our group. We'll look here. I'm going to agree with the propyl part, which is going to come from our alcohol there. And we do have 2 carbons here, which is going to give us our ethanoate. So just like when it's drawn in line structure as well, sometimes people overlook the carbon, sometimes at the carbon-oxygen double bond. So you want to make sure that you do account for that when you're counting them. Question on any of those there. All right, so as I mentioned before, esters are responsible for a lot of sort of aroma and fragrances that we see a lot. Small esters are volatile, which means you can smell them really easily, which I think is kind of like the lab this week. Put them together and don't have too much of the chemicals, but you should be able to waft them towards you safely, hopefully. So as you can see here, these are all esters, and they're responsible for sort of our flavor odor of pears, banana, oranges, pineapples, apricots. And again, all of them can be broken there. And again, going away our alcohol part. So we can see our propyl, our pentyl, our octyl. And again, going the other way will give us our base of the name and ethanoate on most of those as we go through there. So you'll make some of these, perhaps smell some of them, and they're all made from that esterification reaction. All right, so draw the condensed formulas for each of these, and let me just add a few extra just for fun, maybe. Let's do 2-ethyl 3-chloral pentanoic acid. And let's do a butyl. I don't know. We'll start up on top. Why not? So pentanoic acid, oic acid tells us it's carboxylic acid. Again, the pentane tells us it's 5. So we'll start with that. 1, 2, 3, 4, and 5. Once again, since you're drawing, you could put the carboxylic acid on one end or the other, but it again does need to go at one end or the other. So I'm going to put it over here to the right because I could squeeze it in there, I think. So that means for me, that's going to be carbon number 1, which means here going to have a chlorine. We'll go above it, maybe. Chlorine. And at number 2, I'm going to have an ethyl group. And now I'm just going to fill in some hydrogens. So I need 1 there, 2 there, and 3 there. Any questions on that one there?
The calcium started the carbon.
Yes.
So,
Right here, 1. Is that what you're asking? Good. Yeah. That was good. Thought maybe I did. It could have been me. But yeah, so it would, we don't need to give the number, but that should be number 1 where we put it. Obviously, if you put it on the other end, then your number 1 carbon would be on the left there, as opposed to the right. All right, then same thing here. Oic acid tells us again it is a carboxylic acid. Butane is 4 carbons, so in this case we're just going to roll with 4 carbons here. 1, 2, 3, 4. And again, just to show you, if you wanted to, you could put the carboxylic acid over here, and I'll put it on the left here in this case. Because I threw it over here, that would then make this guy carbon number 1 for me. Obviously, if you put it on the right-hand side, your 1 is over there still at number on the right. That means that carbon number 3 for me would be right about there. And now we would fill in our hydrogens to get carbon to 4. And that's it, I think. Any questions on that? Obviously, if you put the group on the other end, it looks just like mine, to just turn around, basically, yeah. Any question on those 2? Coming to the third one, ethyl propanoate. OE tells us it is an ester. Now, we might have talked about this last time, but if not, in this case, since there is sort of a connection part of kind of 2 things coming together, sometimes it might be easier actually to start with just the functional group here. So if I was going to draw this, I would probably start with just the functional group. So I would do this, which I know is basically our functional group. And I know kind of going away from the double bond should be my alcohol part, which is the first part of the name, which is ethyl. So I would put my 2 carbons going that way. And going the other way would be my carboxylic acid group, which is 3. Now here it's important to also remember I already have a carbon going that way. So I want to put the correct number. I don't want to put 3 more. I want a total of 3 so that I do end up with only 3 on that side. Now I can just fill in my hydrogens and 2 there and maybe a 3 back there. Any questions on that one there? So again, with the ester, because you do have that kind of oxygen in the middle of your carbon runs, sometimes it's easier just to start with that and just kind of build out both sides. Or you could do it the other way as well. That will bring us to butyl octanoate. Oh, bad choice. So that is also an ester. So I'm gonna start with erasing. So I got some room, I think. That's where I'm gonna start with. Starting erase up here. All right, so we're gonna start with, once again, because it is an ester, and like I said before, you got that kind of important functional group in the middle where you do have that oxygen that sort of comes in. perhaps is a good idea to start with that. Again, going towards the single bonded oxygen, which would be in that direction, or away from the double bonded oxygen. That's going to be our alcohol part, which is the group name, and that means 4 carbons. So 1, 2, 3, and 4. Going in the other direction through the double bond there, going to give us our 8. And I already got one, so I'm halfway there. Not really, still not halfway. Now maybe I'm halfway there. I'm just really drawing carbons. I hope I hit 8 there. 1, 2, 3, 4, 5, 6, 7, 8. And that's a lot of hydrogen. So let's just drop some hydrogens in here. So we'll go 3 there, 2 there, 2 there, 2 there, 2 there, 2, 2, 2, 2, 2, and a 3. Any questions on that one there? Yeah. All right. Fun with esters and carboxylic acids. So obviously you need to be able to draw them, need to be able to write the proper names, do the esterification reaction. Any questions on any of that there? Okay. So with that being said, let's talk about some other reactions that esters undergo. So as you might imagine, um, if you could put a ester together by taking out water, you could basically break apart an ester by putting water back in. And again, that is basically the opposite reaction. That's the hydrolysis reaction that involves water. Ethyl acetate, which is again ethanoate, ethyl ethanoate, is our nail polish remover. And once again, ethyl ethanoate is the same thing as acetate. Again, that comes from acetic acid, which is the same thing as ethanoic acid or acetic acid. Now, there's 2 types of hydrolysis reactions that we will see. One is an acid hydrolysis, which means it's catalyzed through the use of an acid, and that's what we see here up on the arrows, our H plus, which is our acid catalyst, along with our heat. And we're going to take our ester and we're going to add water here as H and OH here, and we're going to do our acid hydrolysis. So just like we put it together, it's going to really break apart at the exact same location. So that is still going to be our single bonded side. And just like we think about it when we're naming, to the right in this case here is our alcohol. And to the left is our carboxylic acid part there. So just like we sort of think about it in terms of naming. And in a acid hydrolysis, you actually get back both of those things. So it is sort of the direct reverse of the esterification reaction is doing an acid hydrolysis, which means, frankly, you just break apart your ester. And at this point, you basically just rebuild your carboxylic acid and your alcohol. So in order for this guy to become an alcohol, he just needs an H. So we drop an H in there. And conveniently enough for the other guy to become a carboxylic acid, he needs an OH. And we drop our OH back in there. And we get back our carboxylic acid and our alcohol. So the acid hydrolysis is basically adding water, and it's really just the direct reverse reaction of making an ester is breaking it back apart. And you do get back, like it shows here, both parts of it, the carboxylic acid and the alcohol. Any questions on that one there? Now, the base hydrolysis is a little different. So if you take an ester and you react it with a strong base, you get a saponification reaction, which is a fancy way of saying you just made soap, basically. Is basically what that reaction basically is. And it does work similar to the one we just saw. This is going to be base hydrolysis because we are using a strong base. You still have a little bit of heat as well. The difference is when we take our ester in this case, we'll think of it like this, Na and OH, if you will. In this particular case here, we are going to still break it apart exactly where we broke apart the other one. We're going to drop it right there. And that's going to give us here our carboxylic acid part, and that's our alcohol part. Carboxylic acid part. Now, in this case, we actually still get the alcohol back. And if you want to just kind of keep track of things, we're going to actually take the H there and we're going to use it to rebuild our alcohol. Now, the problem is we're not adding water, which is another H, which is kind of necessary for, along with the acid, by the way, it's kind of necessary to make your carboxylic acid because you need to put an OH on it, right? But if we just look at like sodium hydroxide at this point, we pretty much got rid of an H plus, which basically means we have NaO minus, and really Na plus and O minus. And this O minus will then come over here to our positive carbon, and we will get basically a salt, and the sodium will be there hanging out as well. So we will actually get a carboxylic acid salt in this case, and we will get the alcohol back. So going the base route, you do not get both things back completely. You get a salt, which is almost like a carboxylic acid, missing the hydrogen. It does have a charge, which is why it's a salt. It will have like a sodium, potassium there as well to balance out the charge, and you will get the alcohol. This is basically what soap is. If you have a much longer chain of carbons and oxygens. So when you do that and you create something where there's a lot of carbons, I won't draw a lot of them, but that's sort of a lot. You'll end up with this at the end, and this is what is, even longer chain of carbons usually going in this direction. This is what basically soap is, and there's two parts of soap. There's this part here, which is usually a lot longer as well, and that's a nonpolar part of soap. And that's because it's all carbons and hydrogens, which are nonpolar bonds. This part up here, and that's what it's sometimes referred to as a nonpolar tail. This part up here is what is referred to as the polar head of soap. And because it has both of these parts, that's what actually makes soap very good and works very well. And that's because when you have something like dirt, dirt is essentially nonpolar. So what happens is when you put soap on, the nonpolar part, I'll just use this squiggly lines to represent the badly drawn carbons and hydrogens there. The nonpolar part of soap will basically surround the dirt because nonpolar, like dissolves like, so they'll mix really well. What that does is it makes a micelle, which allows the polar side of soap to actually be on the outside. So a bunch of soap molecules surround your dirt and oil because they will mix really well. It aligns the polar side of soap on the outside, which is really good as well because typically when you wash your hands, for example, with soap, you then wash it after you put the soap on, you wash it off with water, which is polar. And the water, when you do that, will then be attracted to the outside part that has the dirt trapped in the middle, but the outside part is polar, so it'll mix really well with water. Out goes the soap that has your dirt trapped in the middle, and that's basically how soap works. It's a good thing to know, I suppose. Yeah. Any questions on that? So that's essentially what you're making in this reaction here. Usually, though, in this reaction here, the sulfonification reaction, usually when it is soap, it's a much longer chain of carbons and hydrogens out going on the other side. So this part is usually a very long chain of carbons and hydrogens, but that is what you get here. So two types of hydrolysis reactions involving esters. They both basically break it apart into a carboxylic acid and an alcohol, except acid one you do get back in both completed. The base one, you get back just the alcohol part completed. but you do make almost a carboxylic acid, but you make a carboxylic acid salt. It just means it's missing that extra hydrogen that wasn't there from like the water and the acid that was present. Question on that there. All right, so why don't you try both of these, write the balance equation and draw it out of what you get when you do methyl ethanoate, and you do it with water, heat, and acid catalyst, and you do it on the bottom there with a little potassium hydroxide, which is a strong base. So 2 different reactions, see what you get. It's an ester, and we're going to start with our ester group here to draw it. And again, methyl is going to be 1 carbon, and ethane is 2 carbons, which means we got 1 more there. So that is what we are starting with in this case. We're going to do the acid hydrolysis here. So that's going to be water, which is kind of like an HOH situation here, a little H plus and some heat happening. Once again, this is the one where we're going to break it apart, and we're going to basically get back everybody because we got all the parts, I guess, in a sense, if you want to think about it that way. So we're just going to simply break it apart where I did the line, which is exactly where they come together. And really, I wouldn't change anything other than now I just need to kind of build out the 2 things I need. I'm going to borrow an H here to give this guy the alcohol. And I'm going to borrow the OH there to give this guy the completed carboxylic acid. And then we should be good at that point. Yeah. Any questions on that there? So once again, basically using the water here to recreate both parts of how it comes together. Again, this is, as we were talking about, pretty much the identical reverse reaction to putting it together. All right, now the second one is going to start with the same thing. So we'll start with our CH3, C double bond, OCH3. In this case, we're going to use KOH, which is a strong base. So this is going to be a base hydrolysis. Doesn't really matter. It's going to still break apart right there. So we'll get our 2 parts. We'll do a CH3, C double bond there. And we'll have a OH, OCH3 there. Now, in this case, once again, because it is the base and we really don't have the water or the acid present in this particular case, we are not going to, again, get back both parts, but we can still get back one of the 2 parts, and that is going to be our alcohol part. So you can think of it as just borrowing the hydrogen there to do so, and that's going to give us back our alcohol. What is left when we do that is really an oxygen that is negatively charged and a potassium that's positively charged at that point. And that negatively charged oxygen is going to be attracted. Remember that the carbon here is actually more positive than the oxygen double bond on top is more negative. So that negatively charged oxygen is going to be attracted really to that carbon. And a lot of times we will draw the potassium next to it, and that's basically a salt of a carboxylic acid, and we'll get the alcohol back. So again, in the base one, that is what we end up with. In the acid one, we end up with pretty much what we started with, both parts completed. Any questions on that? Yeah.
Salt and keep applying heat. Does the potassium and the salt be separate, or are they connected together? If we keep applying heat.
There's still, it's still really an ionic compound, so they will never be like, if you're asking, will they ever kind of bond and share electrons or something like that? They won't. This is as close as they get. So it's still just like a normal ionic compound that we talked about before. What holds them together is that attraction of the charges, basically. Other questions? Yeah, or no? Yeah. Oh, no. Yeah. Other questions on that? All right, so you do obviously need to know these 2 reactions of an ester, one basically the reverse and the other almost the reverse, halfway there. All right, so that's what we end up with there. All right, moving on to the final 2 organic groups. We're going to talk about amines here, and these are nitrogen containing groups. So the functional group here of an amine is a nitrogen here. It's the functional group. And amines, as you can see, maybe from NH2, which is again sort of the functional group there, is really derivatives of ammonia. So these amines really come from ammonia. And a reminder that ammonia is NH3. So a lot of amines are basically ammonia derivatives. They're lacking one hydrogen here, but they still have those non-bonding electrons there on the nitrogen. So they're basically kind of come from that. They contain a nitrogen attached to one or more alkyl or aromatic groups. So in this particular case, because the functional group is a nitrogen, there are some things that do develop because of that, because some of the groups are attached to nitrogen versus carbons. We'll talk a little bit about that in just a second. So these are all amines. Pretty much every time you put on a group, if you will, that's a carbon type group or whatever it may be, you lose a hydrogen. So here, this is a nitrogen, has 3 sort of carbon groups attached, has no hydrogens there. This guy has 2 carbon groups with 1 hydrogen, and this guy has really 1 carbon group with 2 hydrogens. You probably could imagine, but we can classify amines as primary, secondary, or tertiary, kind of like we do with alcohols and carbons and all those things. In the case of identifying an amine as a primary, secondary, or tertiary, we're actually looking at the nitrogen in this case and how many carbons are directly attached to the nitrogen. So we're looking at the nitrogen and basically how many carbons basically are attached to it. So this guy would be a primary, secondary, tertiary. It would be because it's got 3 carbons attached to it. This one here would be, it would be a secondary as it's got 2, and this guy would be a primary as it's got basically the 1 carbon hanging out there. So we can classify our amines, like I said, like our alcohols and our carbons. In this case, we do actually look at the nitrogen and how many are directly attached to the nitrogen carbons. Again, sometimes people, like everything else I've mentioned before, will sometimes teach you to look at the hydrogens. But again, if you look at the carbons, it's the same number of carbons as how many it is primary, secondary, or tertiary. And that's what we see here. Again, a primary has 1 carbon group attached, secondary 2 carbon groups, and a tertiary has 3 carbon groups. Now, the way we're going to go about sort of naming these, as we will talk about here in just a second, is we're going to kind of do name them by groups. So this is methylamine. It has, again, 1 carbonate group attached as primary, 2 carbon groups attached, dimethylamine, and 3 carbon groups attached, which is trimethylamine in this case. Again, naming the groups and just putting amine at the end is one way that you can name an amine. I think that's the way your book does it, so we'll go with that way, I think, in this case. So as I mentioned before, simple amines, we just basically name the groups that are attached to the nitrogen, and we kind of put the alkyl groups in alphabetical order, and then we just simply put amine at the end of it. So as we see here, there's just 1 group attached, so that's going to be ethylamine. Here, looking at the nitrogen, so this is very similar to what we do with ethers. Kind of go to the oxygen, go left and right. Same idea here. Go to the nitrogen and see what's attached to it. Methyl group, so dimethylamine. Here, ethyl group, methyl and methyl. So this is ethyl dimethylamine. Once again, we go alphabetical regardless of the prefix. The di is there because there's 2 methyl groups in there. So we're looking at E versus M when we do alphabetical here. And again, that's why it is in that order. Any questions on those there? Yeah. No.
The second one.
Yeah.
Why is it like NH and not NH3? Why are the 2 electrons different?
Why is
100.
it is so these are derivatives of ammonia. So every group, carbon group that's attached, you lose like a hydrogen. So ammonia kind of starts like this. So in this case, we put a carbon group, so that leaves a hydrogen and
So when dealing with ammonia, we will never have 4 or 5 bonds.
yeah. So if you're asking, should we have like an extra hydrogen up there instead of the not, we will not. So because it's based off ammonia, those are non-bonding electrons, and it's actually really important. It's what kind of gives it, makes it polar as well, like a polar molecule. It's that unsymmetrical sort of geometry that happens, and that's really important because something like this can hydrogen bond, right? Because hydrogen bonding could happen between a hydrogen, nitrogen, and oxygen or fluorine. And in this case, that nitrogen has the ability to hydrogen bond. So that helps it with certain properties and why it might be soluble, say in water and stuff like that. So those non-bonding electrons do have to stay there with the nitrogen in that case. Other questions? All right, so why don't you name these guys here? Look, and again, usually in our case, non-bonding electrons aren't really drawn on these, but they are assumed to be there on the nitrogen when you do see these amine groups. In this case, we basically have just one group attached there, and that's a 3-carbon group. So that's going to be a propyl, and then we're just going to put amine at the end of it, as that is our amine group here. That would be a primary, secondary, tertiary. That is a primary as it's attached to one other carbon, basically the nitrogen. Here, we would go to our nitrogen methyl group. So that's a little dimethyl action happening. We also have an ethyl group over here. So again, alphabetically, we're going to go with our ethyl dimethyl amine. And this is going to be a tertiary one. Yeah. Any question on those there? Okay, we're going to continue on here. Any questions on this so far? All right, so we have a primary amine and a tertiary amine, and we're going to go with mainly here pretty much common names for amines. There are other ways to name amines. There's systematic, there's IUPAC way of naming. Just to give you an idea as well, some things that are a little bit different, which we will come across here, I think, in just a second. And this is, for example, if we have, we want to go more of a systematic name for this. Sometimes what people will do is they will take the longest carbon chain, which happens to be propane here, and they will drop the E and then put amine there and also give the location of where that is. So a systematic name for this primary amine is 1-propanamine, and the 1 means it's on carbon number 1 here, the longest group. We will go with, though, sort of the common name here for us. Now, to also show you that you might come across sometimes another way of naming these guys, again, a systematic way of naming this tertiary amine is actually to look at the nitrogen, and we have these 2 groups here, which is our dimethyl groups. Once again, in this case, this is going to be our longest carbon group that's attached there, which is 2, which is based off of ethane, and this would be ethane amine. Now, normally we would give the location of these groups with numbers, right, if they're attached to carbons. But in this case, they're not actually attached to carbons, they're attached to nitrogens. So you may see sometimes people do something like this, maybe N dimethyl. And the NN means that those groups are on the nitrogens. And just like if we had 2 groups on the same carbon, we'd give the number twice. That's what the 2 N's are there for. It just tells you that those groups are on the nitrogen. So if you see something like this, where there's like N something or NN something, that means that those groups are attached to the nitrogen here in an amine. And that's a very common way that these are sometimes named. Once again, for our purposes here, though, we will roll with the common way that we talked about there before we stepped away. But in case, sometimes you still see that. And we'll still see it, I think, here with the common name with some aromatic ones. But Again, if the group's sort of attached to nitrogen, sometimes people will use an N instead of a number, kind of like what we do with carbons. Any questions on that there? Speaking of that, there it is. I knew it was coming up. If we do have amines that are attached to a benzene ring, like we saw earlier when we were talking about benzene, that is what is known as aniline, right? So this whole thing here is aniline, and that's one of those historical names. Remember that we would use that as the base of our name. And where the nitrogen is attached to the ring would be carbon number 1 for numbering purposes. And in this case, we would want to go, obviously, whichever way we'll give that guy the smaller number. I think it's a tie in this case, left or right, no matter which way you go, it's going to end up at 4. So that is 4 bromo aniline in this case. And in this case, as we were just talking about, this is basically aniline here. And that is where the base of the name comes from. We do have this little line hanging out here, right, which is a methyl. And once again, as we were just talking about a second ago, that methyl group is not attached to a carbon. It is attached to the nitrogen. So that is why it is called N-methylamine. The N meaning that the group is attached to the nitrogen and not the carbon. So again, that's what that N represents in that case. If you had another methyl group attached to the top of it, that would be where we do like the NN that we just talked about, dimethyl, aniline in that case. By the way, also sort of a systematic name for, or a common sort of name for this, with a amine group that's benzene. So that's benzenamine. Benzylamine is sometimes what that is referred to as well, as sort of a common name. So why don't you give it a go here and see what you come up with? Yeah. I hope so. It's okay. You remember everything I said. It's all right. We're good. Yeah. Oh, good. All right. Let me just repeat everything I just said today. We'll just start again. No, we should be good. You don't remember what I said? I mean, I see people writing things down, or just like drawing pictures over there. All right, so there we go. All right, so we're looking for common names for each of these guys here. Okay, so let's take a look. So once again here, we're going to really take kind of like the ether approach. So we're just going to go to the nitrogen and really just sort of see what groups we got going on. So clearly above there, we have a methyl group. That looks like a 2-carbon group. So that's going to be an ethyl group. We got another 2-carbon group over there. So that's going to be an ethyl group. So we got 2 ethyl groups. So it's going to be a diethyl, methyl, and amine at the end of it there. And coming this way, that is going to be our aniline. And that means that we do have this group right there. So aniline. And that is an ethyl group. Once again, it is attached not to a carbon, but it is attached to a nitrogen. So that's going to be an N-ethyl aniline in this case, right? Any questions on those names? First one is a primary, secondary, tertiary alcohol. I mean, it is.
Not connected to the aniline. If it was not connected to the nitrogen, do we still have to put the N?
You would not. You would need to give if it was attached to. Are we talking about this one? If it was like attached to the ring or something like that, yeah, you would need to give the number in that case. So if it's attached, we'll just say it was thrown here. Obviously, that's not it, but it would say it was thrown there. This would then be carbon 1, and then you would want to give it the smallest number to wherever it is. So if it was attached to the carbon ring, then you'd have to give a number for it. But because it's attached to nitrogen, what does happen with these amines, you would use N sometimes. Other questions? All right, so first one is primary, secondary, tertiary. It is a tertiary. Second one is it is a secondary, yeah. So it's got a carbon there and a carbon there, right? So again, it is a secondary amine on that one. Any questions on those there? To draw this in line structure, you do obviously have to incorporate the nitrogen there into your line structure to indicate that it is. This here would be a primary amine, right? As that's a carbon right there that's attached to. This guy right here would be a secondary amine right there. And again, we have 1, 2, 3, which is propyl, and 1 and 2, which is ethyl. So that's our ethyl propyl amine. This is a tertiary amine, 1 carbon, 2 carbons, 3 carbons right there. And again, in this case, that is 2 carbons, which is ethyl. That's another 2, which is ethyl, and that's a methyl. So that's our diethyl methyl amine that we just talked about there, which is a tertiary. So you do need to include the nitrogen. You also would need to include the hydrogen if you drew a line. If you did not put the hydrogen there, it would imply that it's a methyl group, right? So if, in that case, you do need the hydrogen there. Let's talk a little bit about solubility of amines. Primary and secondary amines with less than 6 carbons are typically soluble in water because they can easily form hydrogen bonding with water molecules. So remember that, as I mentioned before, you got your primary, secondary amine, and we have water, and we have negative, positive, kind of positive, negative, and we could do a little hydrogen bonding right there, and it's going to be able to interact well with water. Tertiary amines can hydrogen bond only with water molecules, and primary and secondary hydrogen amines primary and secondary amines can hydrogen bond with themselves because they have hydrogens, and tertiary amines can do the same thing. We'll do that. Here, let's do carbons. And once again, it can hydrogen bond using hydrogens, using water's hydrogen to hydrogen bond there. I'll spit that out correctly here. It cannot, though, tertiary amine cannot hydrogen bond with itself because it has no hydrogen to do that with, so it cannot do that. Now, secondary and primary guys can hydrogen bond with itself. So with that being said, it can hydrogen bond with itself, but it's not as strong as the hydrogen bonding that we see in alcohols. So in terms of boiling points and melting points, amines fall below alcohols, but obviously greater than alkanes that cannot hydrogen bond. So they do fall kind of in that area. Also, primary and secondary amines have typically higher boiling points than tertiary amines, because again, tertiary amines cannot hydrogen bond with itself. So those primary secondaries are going to have a much stronger bond with itself, which will relate to a higher boiling point. So that's sort of where they fall. They fall sort of, we got our alcohol, right? We got our carboxylic acid. Our amines sort of fall below our alcohol, but definitely above alkanes in terms of boiling points and melting points in terms of that. So they do have the ability to hydrogen bond, but not as strong as alcohols. Yeah. Because amines, as I mentioned, has a nitrogen hydrogen bond, they could hydrogen bond with water. So we do get those primary and secondary guys being very soluble, but much like all other organic things, if you build out too much carbons, it's going to start to decrease that solubility. So that magic number kind of ish in terms of solubility with organic guys is like the 5-ish range. That's where you start to see the solubility start to drop for a lot of things. In terms of 5 or more carbons, we'll kind of do that as well. So if amines with 6 or more, again, it affects it, and it's really the same idea. There's just too much stuff routing everybody, and it's going to make it really hard for sort of water to get in there. It's going to cause some steric hindrance, and it's going to make it less soluble in water by a lot because there's just too much going on there, and prevents water from sort of efficiently getting in there and interacting with the nitrogen. All right, so which of these following should be soluble in water? Will the first one be soluble? Yes. is a primary amine, right? So it definitely has the ability to hydrogen bond. So I'm going to go yes on that one. It's got the ability to hydrogen bond, which is pretty much the answer for why something is soluble in water. So if it has that ability to hydrogen bond, that's pretty much the deal there. So that's our primary. This guy here, which is also an amine, and that is a secondary amine. So it also should be able to hydrogen bond and be soluble. That's a alkane. Is it going to be soluble in water? No, right? So again, that's an alkane, right? That's going to be, as we talked about a while back, going to be using dispersion forces. Obviously, water wants the hydrogen bond, so not going to work very well together. Any questions on that there? All right, so let's talk a little bit about reactions that amines can do. So since they are really ammonia derivatives, and ammonia, as you might remember, is a weak base, not surprisingly enough, they do sort of act as a base when they react with water. So ammonia, as well as primary and secondary amines, will act as a Bronsted-Lowry base. I remember that Bronsted-Lowry base is something that will accept an H+. So in this case, it's going to accept the H+ from the water. The result of that is we will get the production of hydroxide, which again is why it's considered a base, as it's able to produce hydroxide in this particular reaction. So methylamine, for example, there, reacting with water will act as a base, accept an H+. It will make an amine salt that we're not going to worry too much about its name. And it works the same way. Remember, as we talked about with Bronsted-Lowry sort of definition, remember, it's not just the H that's moving, but the plus part of it's important in terms of the charge. So whatever's gaining the H+ will have an additional positive charge. So you got to adjust it. Anybody that loses the H+ will become one more negative. So that's why we see water here lose the hydrogen and become one more negative to make hydroxide. We also see here the NH3 becomes one more positive because it accepted it. Same thing here. It accepts the H+ right there and becomes one more positive. So you got to make sure you adjust the charge in this type of situation here. Now, we do make what is sometimes referred to as an amine salt as a result of that. It's responsible for some of the odors that you see in fish, and you can neutralize it by an acid through the Bronsted-Lowry definition, which is why you squirt some lemon and stuff on that stuff. Neutralization of amine salts works kind of the same way here. We will make our amine. It's going to react here. It's going to accept the H+, and that's going to make our amine salt. And what's happening here is still the Bronsted-Lowry definition. If you just think about it like this, we added an H+ basically to this guy. Everything is exactly the same, except there's one more H and a plus. And when we get rid of the H that came from the acid, we're left with the Cl-. And again, this is a salt, which is again an ionic compound in this case. If you react this here, we get the same idea. This is dimethylamine. This is a secondary amine. Same thing going to happen here. The acid's going to send its H+ over. That will go away and make our chloride. And we're basically just going to pop on another H+ there where our nitrogen's at. So that's where it's going to accept basically the H+ from water and also accept it from an acid as well. So it will accept it as well in that situation. Now, properties of ammonium salts, they're usually converted to their ammonium salts before used in drugs. They are solids at room temperature, odorless, and soluble in water. Some of these guys are used in medication like ephedrine. As you can see here, here's some of our ammonium salts parts there happening in each of those things. And our Benadryl right there on the right. Also, ammonium salts are part of cocaine as well. I never know when that question, I suppose, comes up. But we have some of those ammonium salts happening right about there. Are you going to ask to draw cocaine? No. See, that seemed like the right answer to say. Am I still recording? I am still recording. You will not have to name. You will not have to name ammonium salts if that's what you're asking. No. No.
We can
those like boat conformations and those type of things. Yeah, no, you don't have to worry about those for here. All right. These guys here, you're talking about like that part of it? Yeah, you don't have to worry about it. Yeah. I'm gonna say no. It looks scary. I don't want to know about it. I don't really know organic, so I'm just going through it as I know. Alkaloids are physiological compounds that do contain nitrogen. So like our nicotine here, again, some of these ammonia derivatives here, adrenaline, it raises the adrenaline levels in blood, heart rate as well. Caffeine also, an alkaloids here, which are amines. And again, we have our amine groups here, nitrogen containing groups happening. Morphine as well, as you can see, some nitrogens. You do need to draw that. No, I'm just kidding. I'm just kidding. She's like, you don't have to draw that little guy, but that big thing with all the things, you gotta draw that. I'm kidding. I'm kidding. All right, draw these though. These. Okay, so let's take a look. So on these, I would again sort of draw this probably with a functional group first, as we know it's an amine, so it's got to have a nitrogen. And since we're using the common way of naming it, then we could kind of just put our groups on either side of the nitrogen there. So propyl means I need 3 carbons, and methyl means I need 1 carbon. Now we can put our hydrogens there. So that's going to be a 3. That's going to be a 2. That will be a 2. That will be a 3. And do I need anything else? What about the nitrogen? Actually, I actually do need 1 hydrogen here. So you would need 1 hydrogen here. And that's because this is a secondary amine, which means it should have 1 hydrogen, right? In that case. If we were going to do a little line sort of structure there, you would also start with the nitrogens, probably do a little bit of that and maybe a little bit of that type of deal. And in this case, you could also throw the hydrogen. Let's go up since I don't have room. I could pop there. That's fine. You like put a line with the hydrogen on top. That's fine. It's okay. Yeah. Or you could put on the bottom. Since that's condensed structure, you could just write it next to it as well. It should be okay. Yep. We're gonna go 2-chloroaniline. So aniline is a benzene ring, and probably should have the amine group on it. And by the way, 2-chloral means the chlorine is attached to nitrogen or carbon. It is attached to a carbon. Again, if it was attached to nitrogen, it would say N-chloral. And in this case, it happens as a number, which means it should be attached to the carbon. And in this case, wherever that nitrogen you drew it, that on the ring should be carbon number 1. And in this case, you could go left or right. I'm going to go right, and we'll put our chlorine right there. Yeah. Question on that one there. Yeah. All right. Yeah. Good.
That has to have 3 like bonds in the first one. The nitrogen.
The nitrogen. Yeah. So the way you can think about it, because again, you want to think about it like it's from ammonia. So basically the non-bonding electrons, which is oftentimes not drawn a lot of times in our books and stuff like that, they're there. So you kind of think of it almost like a bond. It's like that takes up one of the 4 that you need. And so for every carbon group that you attach there, you basically get rid of a hydrogen. So that tells you basically how many hydrogens you should have left. If it is a primary, you should have 2 hydrogens. If it's a secondary, you should have 1. And if it's a tertiary, you'll have none, basically. So it should always have 3 bonds and the non-bonding electron pair there. And that's what gets it to the octet rule, basically, to 8 electrons around it. So sometimes people miss it because a lot of times for simplicity, they leave the dots off. So people think like maybe there should be in there hydrogen or something there. But in this case, even if they leave the dots off, there is definitely those non-bonding electrons, which gives us 2 of the 8 electrons it needs to kind of get to the octet rule. Other questions? Yeah, that's what I was saying earlier. If you want to put them in, and a lot of times they won't. That way you maybe won't over hydrogen it if you want with that. It's kind of similar. It's kind of similar to like the ether that we did, although they don't draw it, there is dots there as well, right? So you don't want to over hydrogen that guy as well. So if you know that there's non-binding electrons, it helps you remember not to kind of over hydrogen it. You just put them in there. That way you'll know kind of one's taken up for those dots. Yeah. Other questions? All right. So those are amines. Any question on amines? So amines, you do need to know obviously the functional group. You need to know those reactions, I think, and how to name them. And again, we're going to go with common name for amines. That leaves us amides, dare I say, the final one of the season here. And amides has a functional group of carbon, oxygen double bond, and a little amine action there. So kind of like a carboxylic acid, but it's got like an amine group or a nitrogen containing group. Which you could probably imagine how you make this guy, which is you make it through a carboxylic acid and an amine or ammonia basically will make an amide here. Tylenol, an aspirin substitute, acetaminophen. It's like I'm gonna sleep now. Just don't worry. I'll be done in a second. I'll be okay. Acetaminophen there. I'll spit that out, I think. And again, we can see our mid group. We'll also see amide groups when we look at proteins as well. That's a peptide bond, basically. When amino acids come together, that's sort of the bond that we make when we do that. Amides are derivatives, as I mentioned, of carboxylic acids and the hydroxyl group there of the carboxylic acid and an amine. Not surprisingly enough, it is kind of the same idea as like this esterification sort of deal. If you kind of back these guys out here, we'll do it like this. Actually, we'll turn that guy around a little bit. We'll do that. We'll do that. And we'll do, oops. I'll do that, I think. Take two. Let's try it again. I know it's getting to the end. There we go. Let's do this. Let's do this. Let's do this. There we go. So not surprisingly enough, we're going to take out our friend water here. Yeah. So water is going to go out and going to squeeze everybody together. And we would get something like this. That's going to make our amide bond there. There it is. And water basically here. So basically that is sort of what happens to make these amide groups. We take out water and kind of squeeze them together. We get that carbon oxygen double bond into the nitrogen. And it does depend on the nitrogen there. Kind of the same idea. As you'll see, you could classify amides as primary, secondary, and tertiary as to how many hydrogens you should have kind of going in that direction there. And here we go. We prepare it through this reaction, which either uses ammonia or a primary or secondary amine. We use a primary or secondary amine because if I try to use a tertiary, what am I missing? What does a tertiary amine have that does or does not have? Hydrogen, right? So kind of hard to make water if it doesn't have the hydrogen to give, right? So we will lose the hydrogen here in a tertiary. So that's why they won't go through that sort of reaction. You got to have a primary or secondary that has at least one hydrogen to allow it to sort of bond together. But same idea. So what I just drew there, we're just going to pop off the water here. And frankly, just squeeze these two sides together with the connection being the carbon to the nitrogen as they come together. Nothing else changes. As you can see in the box, that's a CH3, that's a CH3, that's a CH2, that's a CH2, that's a carbon oxygen double bond. In the other box, that's a nitrogen and a hydrogen and a hydrogen. Everything is exactly the same, just took the water out and just squeezed it together. Very similar to the esterification reaction where you take the water out and just kind of bring both sides together here. The important part to remember is the functional group of the amide, which is this connection. So you should have basically that connection when you put them together. So that way you could put them together correctly in case one's turned around one way or the other. And again, sometimes it's helpful to turn one around, how you take the water out, and then you could just kind of squeeze them together. So in this case here, what would be the product? Why don't you draw what you should get in this case? And we have a primary amine. So that's going to give us a formation of an amide. Again, if it's helpful for you, you could kind of just kind of turn this guy around, maybe redraw it so you could kind of see the hydrogens and maybe draw the hydrogens out since, you know, those are going to be kind of involved here. And once again, at this point, what we're going to do basically is just take out water. So that worked out pretty nice right about there. So that's going to take out my water. And we're then going to just put together everything else. And once again, nothing's going to change. So I got me a benzene ring happening. I got a carbon to a double bonded oxygen. I clearly got rid of this at this point. So I'm going to make my connection there. And I should end up with something like that. Yeah. Any questions on that? Again, don't overcomplicate it. And remember, as you can see, pretty much as we've been talking about with all these reactions, you pretty much have what you need to draw on the right-hand side, on the left-hand side. Yeah, so you just got to change that small thing and put it together. Any questions on that there?
Product.
Yeah.
The physical matter of the one, but is it a gas or?
It would probably come off as it'd probably come off as a it would probably come off in a liquid in this case because that's a carboxylic acid. So could you put the nitrogen at the end? Are you talking about could you reverse these or something? Is that what you're asking? So can you draw it like oops, like this? Is that what you're asking? No, you cannot. So the connection has to be like this because that is the functional group of an amide. Otherwise, if you put the nitrogen on the other end, you don't really have that amide bond. So that has to always be the connection. So whenever you're drawing one of these or sort of making one of these, it has to have that carbon oxygen double bond, and that carbon then needs to be attached directly to the nitrogen in order for it to be an amide bond. So it definitely has to go like on the bottom there. Yeah. Other questions?
Products. So you just need a little bit of heat just to break the bonds and make the reaction happen. You don't need like a lot of heat to evaporate the water, right?
You don't necessarily need to, no. There's just needs to be some heat, and in some cases you might need some other conditions like acid or the pH of it or something like that. But you don't have to like torch it if that's what you're asking and totally evaporate. No. So you just need it does depend on the reaction, the conditions, but you don't necessarily need a superheated or anything like that. Just a normal, depending on the conditions, regular heating up, like boiling temperature, that type of thing, or just hot in some cases. Yeah. So it does depend on the stuff reacting and the conditions, but if your question is like, do you have to like really torch it to kind of do that? Yeah. Yeah. No, so a lot of times what will happen is just the heating aspect of it will, and again, some of the conditions will allow, for example, if this was say in a solution situation, it can kind of deprotonate, lose a hydrogen and then gain a hydrogen. What happens a lot of times is when these guys kind of come together, they make it like an intermediate. That's actually what's referred to as a good leaving group. And that's why they're able to kind of, with just a little bit of heat, kind of dehydrate it. So although we kind of simplify it that, we take the water out, there's a lot of processes where that hydrogen actually goes on there and makes like water attached. And then that makes it a really good group that will come off pretty easily with some heat, like you're evaporating off something like that. It is in this case, for our purposes, yeah, it's just one way here. Yeah. Other questions? You obviously can probably send it back the other way, putting the water back in and doing a hydrolysis reaction. But for our purposes here, we're just going to talk about it going in this direction here. Yeah. Other questions? Go. Now, naming these guys, clearly, we don't want to name them. So I'm not going to worry about it. I still don't want to name them. I'm still not filling the naming. I'm still not filling the naming. IUPAC, still not filling it. Not filling it. That's some kidneys. No, maybe. So a little bit about urea is obviously a mid here, as we have that bond as removed from the blood by the kidneys through urine. Barbiturates also are amides, and they have the amide group happening right about there. Aspirin as well. Let's talk about two reactions that amides undergo here. And this we will care about. So there is sort of the acid hydrolysis and the base hydrolysis, very similar to what we were talking about previously. Maybe I'll zoom it up a little bit bigger there so we can see it. So here on the acid hydrolysis, we do have water, and we do have an acid there that's going to be used as the acid hydrolysis here. And when we do the acid hydrolysis, which is sort of to your question, almost like the reverse reaction that's happening here, we do it under acidic conditions with some heat. It's going to break apart right between where they come together. So like normal, we're going to kind of break it apart where they come together. And what we're going to get back here is the carboxylic acid completed. So we will get what's in the box here, and we will take, if you want to think about it, an OH from the water aspect of it, and we will get back to completed carboxylic acid. That leaves us, which there's the OH right there. That leaves us a hydrogen that is there on the water. We also have the HCl that's going to provide a second hydrogen. So we will get, if you want to think about it, 1 and 2 hydrogens coming in, one from the water that's left over, and also one from the acid that's going to help it out as well. And what's left is a chloride in this case. So we will get back, in this case, the carboxylic acid if you do the acid hydrolysis, and you will not get back like the amine, but you will get a salt back, basically an ammonium salt. Will be formed in this acid hydrolysis. If you do the base hydrolysis, same thing is going to happen. We are going to break it between the carbon and the nitrogen. And in this case, we will actually get the amine back, but we will not get the carboxylic acid back. So in this case, we don't get back both of them, like we saw in the one with the carboxylic acid and the alcohol. In this case, we get back one and not the other. So in the base, we get back our amine, and you can think of it as the hydrogen coming in there to get back your amine. And that's going to leave us, much like we saw before, our sodium and our oxygen, which is negative, and that will come back to our carboxylic acid and make a carboxylic acid salt. So in the acid hydrolysis, we get the carboxylic acid back completed, and we make a salt for the amine part of it. And in the base one, we get the amine back, and we make a carboxylic acid salt. So if we had this guy here, do we have one? We'll do that one there. So we'll do So let's just say we have this one here and we wanted to do the acid hydrolysis. So we'll add a little bit of water, and we'll add some HCl and a little bit of heat. And this is going to be the acid hydrolysis. So once again here, when we do the acid one, we are going to break it, or even the base one is going to be broken right there. And we're going to write our two parts. So that, and this. And our other part here. Now, in this particular case here, we will end up with our carboxylic acid coming back. So we'll end up with that here. And we will end up with a ammonium salt that's going to basically happen here. And we'll put on there a couple of hydrogens there to our guide there, and it'll become positive. And we'll have our negative chloride kind of hanging out from our acid. Now, if we did this in the base, and we'll add sodium hydroxide here and some heat. Once again, we're going to break it apart here. And in this case, we will get our amine back, and we'll draw our two parts. And I'll just draw it this way here. So our other part. Remember that we're going to take the H if you want to think about it that way, and that will get us back our amine in this case. And what will be left is our oxygen and our sodium in this case, and we'll get our carboxylic acid salt. So again, in this case, acid hydrolysis of amides gets you back to carboxylic acid completed and an ammonium salt. The base hydrolysis here gets you back a carboxylic acid salt, and you get your amine back, basically, or ammonia back completed. Any question on those two reactions? So in terms of hydrolysis here, in terms of amides, you need to know the functional group. You need to know the acid hydrolysis and base hydrolysis reaction. No naming, so we're not going to do any naming of those guys. And that is chapter 14 in organic chemistry. Yes. Any questions on that? I agree. Let's just clap it out here. That's what I'm saying.